All right, I am back online a little later than I was doing yesterday, but I decided to have my coffee first before I went on live on the stream. Today, I'm not going to be able to put in the same amount of time I put in yesterday and the day before. I do have some work I have to do, and this is partially why I was saying I'm going to try to hold that schedule while I can. So what I'm going to do today is I'm going to study for probably 3 hours. I'm going to take a break, do the work that I need to do, and then when the work's finished, I'll come back on for another 3 hours. I shouldn't be too long, so I'm thinking that I might be able to put in more than the 6, but just depends on how long things take. Just to kind of recap where I'm at, I am now finishing up. I'm in the middle of problem set 9. So there were 24 lectures, 10 problem sets. I've finished all 24 lectures, and now I'm working through the 9th problem set. There's still a lot of time left in the month, so I don't want to give the impression that after the 10 problem sets are done, I'm done and I can go forward. And part of the reason is just that this is a hard class, and for more difficult classes where I am missing some of the kind of prerequisite concepts, or I'm not as strong with some of the concepts as presented, then I'm going to need to do a second pass. So what my plan is right now is to finish the problem sets and then go through all the problem set work that I've done, and then just on a sheet of paper write down basically for every question that I didn't get right, what was the concept, technique, or idea that I was missing from that. Now, sometimes those ideas are going to be pretty question specific. So it was like, oh, well, this was the trick to solving this, and you just had to think of it. I'm not going to worry about those too much, although obviously if it's something that like this is an important trick to know, then I'm going to write it down. However, for a lot of them, the problem would have been solvable if I had understood something. Like if something I was going through, if I'd understood it had been more obvious, then the problem would have been, if not trivial to solve, easier to solve. I would say that a number of the problems I've gotten bogged down on because just the difficulty of doing the calculus of, you have this big, horrible, awful expression and a bunch of things cancel. And if you make a slight mistake in the algebra, they don't cancel, and then you need them to cancel. And so I think those are also going to be a reason why I've had difficulties in the problem sets, but they're going to be less relevant, certainly less relevant for my sort of stated goal of this course, which was to have an intuition about quantum mechanics, because that's purely an issue of calculation. But also for my sort of benchmark, which was to finish the final exam, because the final exam I don't think is going to require as intricate calculus, just because it's under limited time constraints. A number of the ones that I've been doing in this problem set, the last few problem sets, because the integrals have been quite complicated, they've been just sort of like, and put it into an algebraic solver. So for instance, I have this integral that I had to solve, which had r cubed times this r to the 2n minus 2 term times e to the minus 2 and r. And like, this is just a kind of thing that they're like, oh, when you do it, you get this factorial, this. And I mean, maybe it's something that would have come to me if I had done it, but it's definitely not obvious to me that that was the right answer for that particular question. And I think it's just the reason why is that for these questions, a lot of them, you would just plug it into something like Mathematica and get the solution. Now, I'm not too familiar with Mathematica. I have been using Wolfram Alpha, which is kind of like Mathematica for this, although it's a little bit less flexible in terms of programming it. I'm pretty confident Mathematica, I might be confusing with another program, but Mathematica is a paid program that can be quite expensive. And so they would have had it at MIT, and MIT students would have Mathematica. I don't. So to fully get the experience of being an MIT student, I really should get comfortable with Mathematica and get comfortable doing those problems. But that's a little bit on the other end of what my goal was for this particular course, which was to just have some high-level intuition. I wasn't really hoping to end this course with, okay, well, now I can compute all these complicated integrals to solve the exact parameters for particular quantum physics solutions. Rather, it was, I want to have a good intuition about what are the fundamental mathematical structures, and how do those fundamental mathematical structures lead to the things that, make up reality. And so things like operators, things like orthogonality, things like, matching conditions. These are the things that I think are really important, whereas computing exact values is not something that's super important to me. I'd like to be able to do it well enough to pass the test, but I don't think I'm going to push further on those parts of the problem set. So I'm on, which part is this? I think I just finished 2A for the for problem set 9. So let me just switch over here. So yeah. I had finished 2A, this first part of 2A, which was, and this is just this awful integral. I don't quite know whether I want to go and do the r squared term, because it's going to be the same jazz here, that I'm going to just have another r squared, and then, well, I guess the calculation is going to be kind of similar, but there's just going to be an r squared term multiplied against it. So instead of r cubed being here, I'm going to have, so I'm just going to put this 2n over rho naught cubed 1 over 2n and 2n minus 1 factorial. So this is now r to the 4th, if I'm not mistaken. I think that should be the only thing that changes. Again, it's not super obvious to me, because this was what this evaluated out to, which makes sense, because you would be integrating it would be plus 1. I don't know what happened to this r cubed, though, term. I don't know how they canceled here. Yeah, there must be something. It must be the interplay of this and this. I'm not sure, because we got 2r minus 4. Yeah, I really don't know, but I'm guessing it's going to evaluate to this. So let's just look over at the solution here. This is question 1. So this is the eigenfunctions of the Coulomb potential, like, just crazy complicated. I never learned this Laguerre polynomials. I don't have it written down in my notes. So I'm also wondering whether this was something that's coming from a reading or coming from a recitation that I don't have access to. And I think if I go through this here, yes, it's the same thing. And this is just, I'll just put this here. This evaluates to 2 over n ro to the negative 5 to n plus 2 factorial. And then just some substitution around, we should get the same result. So I'm going to just leave this question. And let's go on to question B. Use the above results to show that for large values of n and L, what do we have? So we just need square root of 4 0 squared n squared n plus 1 n plus 1/2. So for large n, we're going to get RO. Well, this is going to be n to the fourth plus, what's this? N to the n squared. This is n squared. So this is, and this is relatively small, directly equals RON squared. All right. Uncertainty in R. So we have R squared minus, oops. I'm gonna need a new eraser soon. This guy's getting pretty dull. All of mine are. I have this eraser, but it's one of those awful erasers that when you erase, it just smudges things and doesn't actually erase anything. I didn't realize that when I was getting them. So, we should have, what is our R squared? It's going to be RON squared n plus 1 n plus 1/2 minus I can just put RO squared, and then this multiplied, this is also going to be n squared, n plus 1/2 squared. So for large n, we can discount these smaller order terms. This is going to be approximately equal to RO n to the fourth. Oops, it looks like an n. RO squared n to the fourth minus no, I was supposed to square this. No, I got the right amount. And then plus 1 n plus 1 squared. So this whole top part is roughly equal to 0 because we have everyone squared. All right. the N. So where do we have our energy level? Do I have it on here for the Coulomb potential? No, but I should have it written down somewhere. Oh, here we go. Coulomb potential is equal to E over N squared. Yeah, I wrote down one of these other problems. Where did I have the energy? Where's the energy operator here? So we have E, and I'm gonna have to go through this again because the ones I have here don't actually specify this. I had E0. I have E squared over rho naught is our E0. And then this is 1 over N squared. I don't know where's the half coming from? Oh, 4N squared. So this is what I have here. So I'm missing them. I guess we can just have the minus because this is going to be minus. So I'm having a factor of 2 here. That's different. So I have E naught over 4N squared. It's E naught divided by, I guess this is, we have, rho. That is, they're using R naught there. I'm gonna have to look at how they solve this because I'm getting a factor of 2 off. Equation 15, we get. Oh, here we go. Okay, so I'm just gonna, they did it a little differently here. there's no solution here, they're just saying, I guess. I mean, you're still having a factor of half. I don't understand. I don't understand how we get the. Like they're not added. All right. Part C. What can you say about the size of a weakly bound state of hydrogen? Is this a quirk of hydrogen, or is this generally true of weakly bound states? I don't know what they're driving at here. Are we trying to show that we've got this n squared R naught? I have no idea. What is the answer here? Okay. Mighty fine structure. Oh, this is just one question. Estimate the leading correction to the energy eigenvalues of hydrogen due to relativistic corrections to the electron kinetic energy as discussed in lecture. Use your results to make a diagram of the energies of the N, 1, 2, and 3 states both before and after, including this fine structure correction. You're getting the numerical values of the energies and remaining degeneracy at each eigenvalue. So let's go over to our where is our fine structure constant stuff? Okay. So we have kinetic energy. M squared C to the fourth plus P squared plus C squared minus MC squared. Okay. And then if we substitute this, we have MC squared 1 plus P squared over M squared C squared minus 1. And we want to Taylor expand this to get our first correction. So let me remind myself what Taylor expansion is. We get f of x. Let's put at 0. Equals to it is Fn 0 divided by, is it this? I think this is the Taylor expansion. Let me double check. Mm-hmm. Okay, this is right. What is our function though in this thing? These are constants. This is the thing being operated on. Is there supposed to be a plus here? I don't think there's supposed to be a plus here. I think I wrote this wrong. Which lecture is this? This is lecture 18. So let me just open up lecture 18. All right. Lecture 18.
The following content is provided under a Creative Commons license.
Let me just switch over here so you guys can see.
Your support will help MIT OpenCourseWare.
And so what are we looking for? We're looking for... Okay, here we go.
Perfect approximation. So let's ask, so the first example 1, is going to be relativistic corrections. Now, will relativistic corrections break rotational symmetry? They can't, right? Because relativity doesn't say this is the z direction. In fact, it does quite the opposite. Relativity, among other things, says don't get too hung up on what's the z direction. But relativistic corrections will not break the symmetry. So if we include relativistic corrections to the kinetic energy, this will change E. Change the energy operator, but it will preserve the rotational symmetry. E with L is equal to 0. So we won't break this rotational symmetry, and so we'll preserve the 2L plus 1. So let's check to see that this is true. Okay. So to check to see that this is true, let's actually estimate out the correction to the energy due to the first non-trivial relativistic effect in the matter. So the first non-trivial relativistic effect can be calculated in the following way: what's the kinetic energy in special relativity of a particle of mass n? So that's easy. It's the total energy is the square root of m squared c to the fourth plus p squared c squared minus n.
Yeah, it's not a plus. P squared c squared. Yeah, I thought that looked weird. Okay.
C squared. That's the rest energy. That's the total energy.
So let me just make some edge. This is total energy minus rest energy equals mc squared, which I'm sure you all recognize that famous formula. Well, little did you know that that's only the first part of the formula. There's this mc squared pc squared, mc the fourth p squared. So
this is the kinetic energy. But this is equal to, well, if we pull out a factor of m squared c squared, this is mc squared times the square root of 1 plus p squared over m squared c squared. minus 1. And now if we Taylor expand this guy, because if the velocity or if the momentum is small compared to mc squared, or mc, I should say, if the momentum is small compared to mc, which is morally speaking at low velocities, the velocity is small compared to c, then this is 1 plus a small number. And we can Taylor expand this to get 1 plus 1/2 a small number. And the ones will cancel, giving us only 1/2. So this is going to be...
Okay. So what are we Taylor expanding there? Let me just listen to him give this explanation again.
This is equal to, well, if we pull out a factor of m squared c squared, this is m squared, mc squared times square root of 1 plus p squared over m squared c squared minus 1.
Zach Granat is asking me whether there is learning on steroids. I don't sell it separately anymore, partially just because I worked hard on Rapid Learner, which was a new program that was designed to overcome some of the flaws in learning on steroids, as well as trying to make a better course. But I do sell the archive of learning on steroids. I do offer it with people who get the full package of Rapid Learner. So it is still available, but not standalone. And part of that's just by design, just because I feel like Rapid Learner is a better course for learning than learning on steroids was. I'm also learning about learning all the time.
And now if we Taylor expand this guy, because if the velocity or if the momentum is small compared to mc squared, or mc, I should say, if the momentum is small compared to mc, which is morally speaking at low velocities, the velocity is small compared to c, then this is 1 plus a small number. And we can Taylor expand this to get 1 plus 1/2 a small number. And the ones will cancel, giving us only 1/2. So this is going to be equal to 1/2 that small number, p squared over mc squared, times, m squared c squared times mc squared upstairs, giving us the first term, which is p squared upon 2m. That's the familiar...
Geez, okay. I need to see something in more depth for that. Let's see if my textbook has, because this is just, he's just blowing through that. Let me see if they have relativistic corrections to the atom in this book here. Relativistic in hydrogen, let's do 542 here. See if they talk about doing this Taylor series. I don't think they derive it here. Okay, there's nothing there for relativistic corrections. So let's see. Let's listen to this again and see what he's saying.
Pull out a factor of m squared c squared. This is m squared. Oh, sorry, m c squared times square root of 1 plus p squared over m squared c squared minus 1. And now if we Taylor expand this guy, because if the velocity or if the momentum is small compared to mc squared, or mc, I should say, if the momentum is small compared to mc, which is morally speaking at low velocities, the velocity is small compared to c, then this is 1 plus a small number.
So we're Taylor expanding this 1 plus a small number.
And we can Taylor expand this to get 1 plus 1/2 a small number.
One plus 1/2 of this small number.
And the ones will cancel, giving us all.
So let me just reiterate that 2 seconds of text here of what he's saying, see if I can understand it here. So we have mc squared equal to, roughly speaking, he's saying okay, so this is the first term, and we're using the property that for this being very small, 1 plus e square root is approximately equal to 1 plus 1/2 of epsilon.
Only 1/2. So this is going to be equal to 1/2 that small number, p squared over mc squared, times m squared c squared times mc squared upstairs, giving us the first term, which is p squared on 2m. That's the familiar classical kinetic energy. Rock on. What's the next correction? The next correction is the next term for this Taylor series, which is going to involve this.
So we're doing this Taylor series, and this is how we're getting it. So I think the idea being that so this was the Taylor series. So what was the Taylor series? Well, let's just try to see if we can reproduce this result as a Taylor series. So we're going to have f plus f prime So this was our f. This was our f prime, right? No. How is he getting the? I don't know how he's getting the 1/2 from this.
Quantity squared, so it can be p to the fourth over m to the fourth c to the fourth times mc to the fourth. The coefficient is a minus.
Let's listen to that again.
2m. That's the familiar classical kinetic energy. Rock on. What's the next correction? The next correction is the next term for this Taylor series, which is going to involve this quantity squared, so it can be p to
That quantity squared. Why is it that quantity squared? Well,
the fourth over m to the fourth c to the fourth times mc to the fourth. The coefficient is a minus 1/8, so we got minus p to the fourth over 8 m cubed c squared.
so
Square root of 1 plus p squared over m squared c squared minus 1. And now if we Taylor expand this guy, because if the velocity or if the momentum is small compared to mc squared, or mc I should say, if the momentum is small compared to mc, which is morally speaking at low velocities, the velocity is small compared to c, then this is 1 plus a small number. And we can Taylor expand this to get 1 plus 1/2.
So let me see if I can write this out. So we've got our function is going to be if it's root x, and we have root x plus, so it says 1/2 plus 1/2 root 1 over root x I don't know where we're getting the square factors here. What is he Taylor expanding?
Small number. And the ones will cancel, giving us only 1/2. So this is going to be equal to 1/2 that small number, p squared over mc squared, times m.
I think there's no other explanation for this, so I'm going to just have to go to the solutions here and look at the starting point of this question. Okay. They're just taking it from the class. There's no explanation of this. Oh boy. All right, use your results to make a diagram of the energies in 1, 2, and 3 states before and after, including the spline structure constant. It's over here. Oh, sheet's getting all wrinkled up. So this is the new energy ion operator. So it's going to be the old one. Minus n squared. Minus what is the change due to this? Are we going to have to take the closed form of this whole thing and multiply it out? What's that? This is going to be a nightmare of a differential equation to solve, so I don't understand how. Is there something I'm supposed to exploit to get it closer? This is p to the fourth. I'll get rid of this in pencil. Whatever. So we're just making an estimate here. For 2 over n rho naught cubed. N minus minus 1 to the minus r n r naught 2 r n r naught times Laguerre polynomials of 2l plus 1 n minus l minus 1 2r m. And then we're going to have, this is just going to be well, this p to the 4th should be IH bar yeesh. But this isn't spherical, so I don't know how this is going to change with. How are we converting it now to, do we have the momentum operator in the spherical coordinates? I think that might have been on problem set 8. Do I need to include a factor of r into this? I think so. So this should be what? IH bar r dr, I think. I mean, the 4th derivative of this mess. This is going to be, oh, this is the momentum operator. Yeah, momentum operator to the forces. I think it should just be H bar to the 4th. I mean, This is a constant. This is going to come down 4 times. This is just going to be the same. We have 1, 2. How many terms have I on? 1, 2. I don't even know what these Laguerre polynomials are. What are the Laguerre polynomials? L and M shouldn't matter, so I think this should just be 1. And this will be maybe we can just consider N 1, 2, 3 states. Yeah, it shouldn't matter. So these can just be what did I have? I can just substitute this over to -1. This will just be 1. I don't know. This seems like a wrong way to do it. Let's see what they're doing here. I'm going to spend all day working through this video. Okay, there's a trick here. NLM in the 4th. NLM equal to NLM. Is equal to what? Well, we have 2m squared. So here we're exploiting this relation, I guess, that because we have E is equal to P squared over 2M. Okay. That makes sense. Why is this squared? Oh, right, because it's a squared. V squared. And, squared. Wow. This has to be the most involved calculation I've seen in the entire class. I mean, this is crazy. Let's walk through it. I have even doubts that I'm going to be able to learn something like this. So we started with, so we didn't go through the explicit form of this equation. Instead, we used just the operator method here. This is just a simple factoring the two p operators. We can p squared operators. We can solve for energy operator and the potential operator. Put those in here, and we've got this factor of 2m squared that gets tossed out here. So we have it twice. And then because we have this e to the sort of original energy value, I'll put it over here, e the energy value squared. So we're going to factor that. We factor that, we get, we not factor it, we multiply it out, and we get three terms. One just has the energy term squared, which is pretty easy. This is just this, because it's energy eigenstate. This one has energy times this potential operator times this. And this is a little trickier. And we have to exploit this relation, which I'm not sure where this came from. E squared over r is equal to minus e divided by 2 dE of this. Oh, okay, because this is going to give us 2 e over r. So this is just an identity. Because when we take the 2 down here, well, this just becomes 1, right? And then this becomes divided by 2 ER. So those 2 cancels, and we have E squared over R. And the minuses cancel. So this is just trivially true. And we know that this is equal to our energy. This is equal to our energy expression, I think. E squared over R. So this is just the, this is just our E hat, I believe. I'm gonna write this in pencil. And because this is energy operator, we'll just get this value out because it's now going to leave this untouched. Okay, so these ones make sense. And now this one, rewrite in terms of L squared eigenstates. So the L squared eigenstates, I don't quite recall this, but we have this formula here. Not sure where we're getting this from. I'm gonna have to look at the lecture again, I think, because a lot of these, like this here, I don't remember this showing up anywhere here. I'll have to look this up. So, and we note that we have these eigenvalues. I'm just going to call this J max. These are our eigenvalues. So where did we get this? 1 over r squared. Where did I put this? Oh. Now observe that 1 over r squared is equal to 2m over h bar 1. I'm not sure where this is coming from. This must just be trivially true, right? So we do DDL. The r squared is going to remain. These are going to cancel. So this is, again, I'm going to say trivially. This is also trivially true. LL plus 1. If we take DDL, this is 2L plus L. This is L squared plus L, so this is going to be 2L. And then L is just going to be 1, so 2L plus 1 is going to be the coefficient that goes down here. So this is trivially true. And then how did we get up here? 1 over 2L plus 1. DDL. So we inserted the So we took this trivially true expression and we inserted p squared over 2m. So this is equal to our energy, right? Our energy operator. What did we do here? We did we just included the energy here. And our energy was 2m over h bar squared. I'm not sure how this 2m over h bar squared, why is that disappearing? I guess in our m we have h bar squared. H bar squared over m. E to the fourth r to the fourth. So I think we're just kind of adding the energy operator and removing it here. And then what happens next? Precisely the energy operator for the hydrogen atom. R squared. So write this in terms of this. I think they just maybe forgot this 2m h bar squared over here. I mean, that seems ballsy. No, that can't be it. You just add these things in for no reason. I mean, it has to come out of somewhere. And then we just added it all together to get this. I mean, this is definitely the hardest problem I think they've had on all the problem sets. There were so many steps here that there's no way I would have gotten them. I'm not even quite sure I understand what they did in the solution in some of these parts. But it's a lot of like observing and simplifying and well. All right. Wow. Wow. 4. Short answer. Clume is not hydrogen. Answer each part with no more than one short sentence and no more than one equation. A hydrogen here, let's agree on a simple model of electron, the Clume potential, which we studied in the lecture so far. Consider a hydrogen atom in its 1,0,0 ground state is the electron in motion. I'm going to say no. Here's why. Why doesn't it radiate? Oh, so why doesn't it move? Theta stationary state for all stationary states. B accelerate. C, consider an hydrogen is the electron in motion. Model because hydrogen, because I'm going to say stationary state, stat state. D, why doesn't an hydrogen same reason. E, experimentally, if we excite it, it will relatively quickly decay back to the ground state. How much angular momentum would our atom of hydrogen emit in the process? Good question. So going from 211 from 211 to 200. Is this what we're looking at? How much angular momentum would it emit? I want to say this is going to be the root of L squared. But what were the energy eigenvalues? What were the eigenvalues of L squared? They were m⁴ over 2h bar squared. N plus L squared. So R two h bar squared. L is 1, N is going to be -2. So we have 2 minus 2, 0 plus L plus 1, which is 2 squared, so 4. So this is 8. this. What wavelength does it have? Ooh, the energy is equal to, well, this is momentum. We can just do wavelength. It's h bar k. So we have h bar divided by is equal to 1 over root this is going to be 2 root 2 over, this is root m squared. I think the dimensions are wrong there, no? This is momentum. I don't know what E is. I don't know whether this is L squared or L. I think it's L. If this is L squared, it would be root of this. So I think this is right. G. What is missing in our model? Corrections. Relativistic. Perturbations. Hermitian. Why can't it be Hermitian? Energy can't be Hermitian. Hermitian means its own adjoint, which means what? I'm not sure why it can't be Hermitian. I think it can't, but because that was easy. Adjoint, and what was the definition of the adjoint? The adjoint was a energy is no longer conserved in the electron. That's my answer. All right, let's see what we have. Da, da, da. Hold on a sec. I think. Hold on a sec. Let me just add this here. So L squared beta and LM equal to H bar squared LL plus 1. Is that what I got? So I go from 2, 1, 1 to 1, 0, 0. Two H bar squared. And HC over H over pi squared. And this should be equal to Okay. Thanks, Jason. Stationary states are well stationary, so they clearly can't radiate. We can, of course, build states in which the electron does move. Okay, so okay, so sort of right. Question 5. Band structure. All right. Run the physics ET simulation called band structure. I don't know whether I downloaded that one. Do I have that one? I do not. So let's download it. All right. Okay, so let me just pop this into our view so you guys can see it. Oh, let me lower this down here. Internal server error. Am I not live anymore? Hold on a sec. All right, it looks, yeah, thanks, Jason. It looks like there's a problem with updating this. I'm trying to, oh boy. I might just reset the feed quickly because I want to be able to show this applet, and maybe I can, yeah, I can't, it's not letting me adjust. All right, I'm just gonna restart the feed. I'll be back in 2 seconds. Okay, I'm back on. I don't know what was going on there. Let me see if I can update it. It was saying it was saying that there was some kind of error. So let me just see if I can pick this out. Let's see if this works. Yes. Okay, we are now successful. So thank you for bearing with me here. So we have this band structure here. It's kind of cool. Now let's look at the, not problem set 8, problem set 9. Run the physics ET simulation called band structure and use it to answer the following questions. Note that the numbers produced in the simulation are correct for a particle of mass 0.511 mega electron volts, the electron mass. You're strongly encouraged to work in groups. Well, goody. All right. I think this question's pretty involved, so I might not do the whole thing. I think that was the idea for, so I might not write them all down. I might just play with them here on the live stream so I can get a qualitative sense of what's going on here. Set the potential to 1 square well in height 18. Oh, so do I want to, oh, what happened here? So this is the solutions. What happened here? Okay. You know what? I'm going to try to see. I'm going to switch from my my camera here. One sec. I'm going to add. This is going to be hard to do both of them, maybe. Let me just see if I can move this around. Let's go. Let me crop this here. And then we want to go like this. And then let's go. Maybe a little bit more cropped here. Let me go just scale this guy down. And what do we have here? And I'm just going to, oh, it's hard to fit everything. How am I going to do this? I'll just scale my window just really small right now. And I'll just add the make this really small. So this is gonna have to do for right now. Let's see if this works. Okay. All right, so now you can hopefully sort of see I'm jamming a lot of stuff onto the video here. It probably won't be for too long. So what do we have? I've got these. I'm just gonna move this guy over here. This guy over here. So set the potential to 1 square well. So we want 1 well. I guess I can just go down to 1. And height. Where's the height? Configure potential. Oh, height 18.2 electron volts. And width 0.4 nanometers. Okay. Oh. Why is this magnifying glass here? Oh. Get rid of the magnifying glass. Verify that there are 3 bound states. There are 3 bound states. Record these values and sketch each eigenstate. So I'm not going to sketch it. I'm just going to look at it. All right. So these are the probability density. I think I want the wave function. Yeah, odd and then even again, which is what we would expect. The tails penetrate further because they're higher up. Keeping the shape of the potential fixed, change the number of wells to 2. Begin with the separation set to the maximum allowed 2 nanometers. So this we want, okay, maximum allowed. Verify the energy eigenvalues are discrete, non-degenerate, and come in sets or bands. So we have 1 here, and then a second one, and we have 1 here, and the second one, 1 here, and then the second one. How does the mean energy of each band compare to the eigenenergies of the single well? So let's just go back down to 1 well and write down what the energies were. So they were, okay, so 1 well, we had E1 is equal to 1.52. What kind of is E0? I don't know why they've got convention here starting at 1, but I'm going to do E0. I just have to make sure I remember that. So E1, 1.52, E2, 5.96, and E3 is 12.84. And now 2 wells. I think we have the distance, yeah. 2 wells are E0 is 1.54. .56 equals 6.03, 6.14, 12.87, and 13.32. So these are slightly higher energy, which kind of surprises me because we haven't changed. I would have thought they would have been lower. Why are they higher? Like, I mean, why are they narrower in this than in the... I would have guessed the other thing. I would have guessed that they would have been lower. Because I would have guessed you could fit why is having the second well scrunch this one up for the lowest energy? Because it does boost it a little bit. This would suggest, if it's higher, that if we moved the wells infinitely apart, that would be at a lower state, right? Which is not what is happening. Like when we did the delta function, the the energy dropped down. Right, 5, 4. Let me just write this again. 5, 2. Because we did the delta function potential, we found that two wells really close together. So if we just consider them arbitrarily far apart, there should be less curvature. So how is this different from the? Oh, that's very concerning. Let's see what the answer they have here. So I'd like to know a solution to this. Note the differences increase with n. Why is that though? I would have expected them to go down. Are these energies negative? No. As you think that the potential wells want to be together. So the energy should be higher when they're apart, right? I don't understand why that's the case. All right, what's the next one? For the top state and bottom state in each band, count how many zeros lie inside wells and how many lie between wells. How are these states related to the wave functions of the single well? What about the other states in the same band? How are they related to wave functions of the single well? So that's going to be this one here. So there's no zeros in the wells. 1 0 outside the well. So this is going to be nodes in well. I'm going to say between well. So this is going to be in each well. One, and then, yeah, 1, 1, yeah, 2, 1. Okay. How does the width in energy of each band vary from band to band? How does the width in energy of each band vary from band to band? It increases. Yeah, okay. Reduce the separation between the wells holding the width and height fixed. How do the width and mean energy level of each band vary as you vary the separation? So it's increasing the band separation. Oh, now it's lower. Weird. So it increases the band separation. Within each band, one state looks nearly periodic with a single dominant period. Which state? What approximate wavelength? Psi. Compute the energy of a free particle of mass m in this wavelength. Compare this to the observed energy of the nearly periodic state. So the top band looks nearly periodic. Which state and what is its approximate wavelength? Psi. So it's going to be the highest state in each band. What is its approximate wavelength? Where did it? Can I see a wavelength here? Do I have wavelength here? Can I see? This is the wave function. Is there a way of showing the wavelength here? Do I have to calculate? Like this wavelength is approximately 1 nanometer. So this is, we'll just do E2 1 nanometer. Can I change the readings on this? How do I? Can I change this position nanometer? I can't. That doesn't work. I mean, it's approximately 1. And then what is the of 1.71? Is it electron volts? What are those energies? I think it must be in electron volts. EV is energy. So we have energy is equal to momentum what's energy and momentum squared over 2m, right? Energy. This is day 1 stuff. That's the expression for energy. Is equal to H bar omega is equal to H over lambda. So we get what is H in terms of electron volts? Is 6.6 times 10 to the negative 16 EV divided by 1.71. So what about it's about 3 times negative 16 meters. I think I'm forgetting a factor of pi here. This is H bar, and we want H out it, so it's H over 2 pi. Is it 2 pi? H over 2 pi. So it's going to be times 2 pi, which is about roughly 2 pi is 6.1. So this is like, yeah, this is about 2 pi. This is roughly 10 to the negative 16 meters, which is how much? This seems wrong. I must have missed something in the calculation. Negative 16. Oh, I'm forgetting the mass. Hold on a second. Maybe just for light. We have
Mr. Scott, what is your mailbox number?
H bar over lambda squared. What am I messing up here? Oh. Okay. Okay, cat. No. Time to get down. Yeah. No. Get down. Get down from there. You discovered a way to get up. Hey. Yeah. Oh, did the cat? Oh yeah. Tilt this a little bit there. Okay. What am I? this is super early on and I'm making a mistake about it. What is this? Energy is equal to 1/2 mv squared, which is energy is equal to 1/2 momentum how do I get the energy is equal to momentum squared over 2m, and our momentum is equal to h bar omega m. So energy is equal to h bar squared omega squared m over 2 should be equal to should be able to just change this to h squared. We can just go h over lambda squared m over 2. So we get equal to square root of h. I don't know, I keep doing the bars. H squared m over e times 2. So we have the electron mass. Okay, so we have h squared, which is going to be 6 times 10 to the negative 16 eV seconds. And then this is our mass, which is 0.51 times 10 to the mega should be 6 eV divided by our energy, what was our energy? 1.71. So you can find the frequency, but I don't know how to do I'm forgetting a C maybe here. Yeah, because this is root seconds. I don't want that. All right, let me just try this again. E is equal to e squared 2m This is root h prime omega. Might be root h prime omega. This is in units of EV times F. This is in units of angular frequency is meters per second. So we should get oh boy. I'm just going to put a note here. Okay. Where is our P is equal to H bar over lambda. E okay, here we go. This should be right. And we can just root this. So we have H bar 6.6 times 10 to the negative 16. And this is EV seconds. And then this is I don't know why I'm getting this. Is not in nanometers though. I'm getting it in seconds. Do I need to use the speed of light? I think I might just have to use the speed of light. Somewhere here. Hold on a sec. This is an electron though. We're not necessarily moving at all. This energy is 1 point. What was the energy? 1.71 eV, and then the mass is 1 point. What is it? 1 point. I'm sorry. This is 0.511 10 to the 6 eV. These roughly cancel. We get 10 to the 6. Root of that is 10 to the 3rd. 10 to the 3rd divided by this. I get equals 6.6. 19 seconds times 3 times 10 to the 8th meters per second. I don't know. I'm just throwing C in there right now. It's going to be 1.8. Oh, no. I'm not supposed to put this 1.71 in here. Oh, and this wavelength. It's 1.8 times. This is 10 to the negative 11. 10 to the negative 11th, which is how many meters? This nanometer is equal to 10 to the negative 9th. So I'm off by a factor of 100, which is not good. So let's see what we have here. So we have EI is equal to H squared over 2 ME 1 over I squared. So this is H is EV times second. Electron volt. I must be missing something here. Mass of electron. EV. Times squared. Let me just try dimensional analysis here. So electron volts times second. Another way of putting this is kilograms, because it's equal to energy times meters, which is equal to F. So this is energy, which is equal to F. It's energy times time, which is equal to F equals ma, mass times acceleration times distance times time. So this is equal to kilograms meters per second squared. Meters squared. Second cancels. And then we have, so this squared, which is kilograms squared, meters, fourth squared, divided by, this is in electron volts. This is also an energy. Yeah, I'm not sure. This is, okay, let's keep going. C, keeping the shape of the potential fixed, repeat the analysis above for 3, 4, and so on. You already make a prediction for the special case of n was 10. Same idea. The highest one is almost periodic. And spacing increases. So we have 10 states. Each one. So what we would expect, predict. All right. D, keeping the shape of the potential fixed, changing the number goes to 10. Okay. The case of 10 wells, make a plot En as a function for n for the minimum allowed separation. So as the separation goes to infinity, all the bands just squeeze back into the degenerate. All right, this is what we... Yeah. So each time, let's see if we can go higher than this. Oh, I can only go 10. So these are just gonna keep... These are just gonna become bands. So, yeah. This is what 100. This will just go all the way through. Yeah. Okay. Oh, that's the end of that problem set. So I'm going to just switch over now. No, I don't want to do this one here. Let's get this right here. Okay. Oh, so that's problem set 9. Really made some mistakes here with this dimensional analysis. This was something that I did a little bit of an analysis of before did a bit of a Feynman technique, but the problem here is not really a conceptual understanding. Of course, I understand what dimensional analysis is. It's mostly just about being able to quickly convert between the units. So I think what I might do is spend some time creating like a little chart almost of how all the things relate. So all the formulas we know so we can convert and compute in different situations. Is in this particular case, I'm getting something mixed up here because this is supposed to be a mass, but the mass is listed in electron volts. So I'm not sure what quite is going on there. So one more problem set. I'm going to start working on it later today. I am going to take a little bit of a longer break in between. So yesterday and the day before, I was kind of just going really quick, like half hour, and then back to work. Unfortunately, I do have some other work I have to do today, so I'm not going to be able to jump right in. So what I'm going to do is take a short break right now, have a quick bite to eat, get to work, try to finish as much of that as possible, and then when I'm done finishing my work, I'm going to switch over and try to work later today. I'm definitely going to put in at least 3 hours. I just don't know whether I'm going to be starting at, if I can start earlier, or whether I'm going to be starting at 2 like I was normally scheduled. We're doing pretty good for finishing all the problem sets. I'll just switch over to this view. I'm doing pretty good for finishing all the problem sets. I've got one more to do. There is a lot of work to be done. I've kind of talked about that before. Some of the work has been done doing the problem set, so I already feel like I've made quite a bit of improvements. But it's not the case how I would say for a class of moderate difficulty, when you've done the problem sets, you kind of know the material. You have a pretty good understanding of the material. This case is a hard class, at least relatively speaking for me. So having done all the problem sets, I do not believe that I have mastered all of the material that it contains. There was a lot of feedback having to get. I was struggling on a lot of the problems. So what I want to do after this is, after I've done all the problem sets, I'm going to go through them all, start to finish, and write down on a separate piece of paper every single concept, every single idea that I'm struggling with. Some of those ideas are just sort of singular kind of things that you just need to understand one idea, and some of them are more elaborate, like I was indicating here with dimensional analysis. That's actually not just a single concept, because it's all about how do you have all these constants, and you have a lot of dimensions floating about. How do you get the dimensions that you need for a problem, but also how do you quickly check that what you're doing makes sense, that that you've got the right units and that you haven't converted things improperly. And so that's going to be something that maybe takes a little bit of practice. So my hope is that I might be able to make some good progress through 10. I looked at it yesterday. It looks pretty long, so that might take me into Thursday working on that. I would like to, at the very least, be finished the problem sets and have my roadmap of what needs to be improved. And then it's just going to be how much can I improve all those foundational points. And then I'm going to work on those sort of drills, at least for a certain amount of time. And then I'm going to want to shift back to doing problems again. I mentioned that 2 of my options are to rework some of the old problem sets. So things that I struggled on, I can tackle those questions again, but without, I've already gotten the feedback, so I should be able to do them a little bit better this time around, because, I've already seen what the answers are. I've already seen how to solve those problems. And so this is more just a test. Do I remember how these problems work? Do I remember how to solve them? Which is also not a trivial thing, especially if they're difficult or confusing problems. However, those are the same problems that I did. So solving those problems again can sometimes, you can memorize, oh, you were supposed to do this, but you don't know what the motivating reason was. And so I try to avoid doing that, generally speaking, but I don't have a lot of options here because I don't have tons of material to work from. So once I'm done, I can either do the second pass through some of the problems in the problem set. I'll probably do a selective pass through of some of the harder questions. But I think what I'm also going to work on is the exams that don't have solutions, because that's going to give me a better sense of what the difficulty level of the problems on the exams are. And then I think I might start there and then work either I have more problems in my textbook that have solutions, but I've already been finding that they don't line up as nicely with this particular class as it is taught as I would like. They introduce some methods in this class that are different. It's just different vocabulary, different terms, and so that's going to create some issues. Not to mention that I've got these exams, I've got these problem sets, I've got different values for those that the actual exam that I'm doing or that I have solutions for is not from this session. So I'm going to have to work around all of those obstacles in taking this class. I don't know how things are going to turn out in the end, but I'm going to try to push as far as I can in this month period of time. And if it looks like I'm not quite there yet, not quite ready yet, I'm going to come up with a plan for what I want to do long term to get there, because after April, I'm not going to be able to put in this intensity. So if it looks like I'm not quite where I'd want to be, I might switch this over to sort of a project of continuing it out into longer, of just doing smaller amounts of practice. But at the very least, I should have a good foundation in how this class is set up, how it works, even if there's some stuff that still requires practice or still requires work. So I'm going to take a break right now. I will be back at it later this afternoon, although I don't know exactly when. So I hope to see you then.